Alright, so in this video I'll show how I've used Microsoft Excel to solve the CSTR energy balance problem that we looked at in the last example. So in that example we had been given information about a CSTR, including about the size of the CSTR as well as heat transfer properties, and some about the kinetics. We used that information. We developed two equations, an energy balance and a mole balance, and in this video we'll solve those simultaneously in Microsoft Excel. So basically what I've done here, I've put all of the constants in these columns. So this is all given information. The one thing I wasn't given and had to look up was this value of R, the gas constant, so I'm going to end up using that in the Arrhenius equation in a little bit. So I had to look this up. The value of R that I'm looking for, that's going to be, it's going to be used in a ratio with the activation energy E. And so since E is given in calories per mole, I want R in calories per mole Kelvin. So again, I want energy units of R, not pressure volume units. The other thing I did, similar to the other types of examples that we've worked, I took all of the units and converted them so that they're consistent. So time units are minutes, energy units are calories. The temperature, everything is per temperature, so some is in Celsius and some is in Kelvin. But since if we're talking about a delta T of 1 Celsius is equal to a delta T of 1 Kelvin, I can just leave those as be. Okay, so a couple things. I'm gonna walk you through the various parts of this worksheet. So what I've done here, I want to solve simultaneously the mole balance and the energy balance, and I want to do that as a function of T. So this column here is basically just temperatures, where I'm incrementally increasing the temperature. So I just specified these starting at 300, which I kind of guessed that arbitrarily. Actually, my first guess wasn't 300. Ends up being a good guess. I started out at like 200. I made my plot over here, and I just kind of tuned this until it gave me until it captured a region that I was interested in. So. But anyways, these are just numbers. I'm just specifying them. This is the energy balance. So this is this expression here. So basically, if you look in this formula, if you inspect this, that's what you would get. It's this energy balance term. So if I click here, for example, I'm using this information up here as well as the temperature to generate this energy balance. So you'll see that at this initial temperature, it's giving me a conversion of -1, so that's unrealistic. But basically what I'm trying to do, I want to make a graphical solution, so I just need points to graph, and I can adjust the axis ranges on my graph, and I'll do that in a minute. So energy balance is pretty simple. The mole balance, that's here. It's not as simple. That's because before I can solve the mole balance, I need to take into account the temperature dependence. The temperature dependence comes from K, which is an Arrhenius equation. So I'm actually going to make a separate column for K and write K as a function of temperature. So K is equal to, we're given a value at a reference temperature. So 0.0066 per minute at 350 Kelvin. And we can use the Arrhenius equation, which is the exponential of the activation energy divided by the gas constant, times 1 over the reference temperature minus 1 over the temperature. So I need to do that before I can write my mole balance. As you see, at very low temperatures, the rate constant is very small, and as the temperature goes up, the rate constant gets very high. So the rate is significantly dependent on temperature. The mole balance, once I have K, then the mole balance is pretty simple. So I can write that in. It depends strongly on K, so I get very low conversions at low temperatures, and as the temperature rises, I get high conversions, and I can achieve nearly 100% conversion at even the highest temperatures. So now what I want to do is I want to plot XEB and XMB. and the point at which the two trends intersect is going to give me simultaneously the conversion and the temperature that this reactor is achieving. So this is the plot. So this actually has 3 trends on it, so we're only going to look at 2 trends for now. So we're not going to look, in fact, we're going to look at the red trend and the green trend. That's this one and this one, and we're going to ignore the gray trend and the yellow trend for now. So looking at this, the red trend, this one, that is the mole balance. So at low temperatures, the mole balance starts out very low and the conversion is very low. At some temperature that lights off and then achieves a conversion of near 1. So the mole balance is very sensitive to the temperature. And it has this S-shaped curve, and the reason it has this S-shaped curve is because of the rate constant. So at low temperatures, the rate constant is very small. There's not enough energy to surpass the activation barrier. At some temperature, around in here, the rate constant, what we call lights off. So all of a sudden, the temperature is hot enough to surpass the activation barrier. Because of that, the conversion shoots up dramatically. So that's my mole balance. Because of the Arrhenius form, it has this S-like shape. My energy balance then is this one. Notice that it's linear. So the energy balance is a straight line. So the energy balance ends up being a little bit simpler, and the point where the 2 intersect, that gives me my answer. So in the problem statement that we had looked at, we wanted to determine the reactor temperature for a feed of 450 K. If we go back to this graph, we see that this plot was, or this line right here, this energy balance term, that was for a feed temperature of 450 K. So if you look at the trends or the values you get here, they're dependent on this feed temperature of 450 K. That means that where this plot intersects the mole balance, that's the answer to that question. And so they intersect right here. I'm getting a conversion of essentially 100%, and the reactor temperature is 400 K. So the feed temperature is 450, and the reactor temperature is 400. So that's how we solve if a problem given, if we're given a feed temperature and we need to determine the reactor temperature and conversion. The other things we're asked for here are the extinction temperature and the ignition temperature. So I've also created 2 different plots here, and I had to kind of play with these numbers. But basically, the ignition temperature, so if you're thinking about this XMB line, so this red S-shaped curve here, the ignition temperature is, if you're operating, is when you would think about an ignition temperature when you're operating at a low conversion. So somewhere in this range here where the conversion is very low. And the ignition temperature is the feed temperature that you would have to achieve in order to start operating at a high steady state. So something up here. So what I'm doing here, basically, I want to create another line, and I'm looking for the line that's tangent to this part of the mole balance curve, because I know that once I turn the feed temperature up hot enough, so if I'm down here, I turn it up, I turn it up, I turn it up, I'm still operating at low steady states, so low conversions. At some point, I'm going to turn it up just a little bit, and the next place where the graph would intersect would be up here. So that's going to be where this line, where this energy balance line, is tangent to this curve. So that happens about right here. So any feed temperature above this, so at this point, my conversion would be on a low steady state. If I turn it up any more, then the next place where I would have a point of intersection would be up here. So I kind of had to play with that. So I started out with different values. So 375, and then I say, okay, that's still giving me, if I'm in a low steady state, or I'm at a low conversion, then I'm still going to get a low conversion. So let me turn that up a little bit more. 390. Okay, I'm still, my first point of intersection is still right here. Okay, let's turn it up a little bit more. Now my point of intersection is there, so I'm getting closer. Okay, so let's go to 410. I go to 410, and yeah, now I'm operating at the high steady state, but that, I need to back off the temperature a little bit because the ignition temperature isn't that high. So back it down to 405. Now I'm pretty close, and then I just kind of backed it down to 404 because now I'm, pretty sure I'm tangential there. So somewhere 404, 405, that's going to be the first point where I land on this high conversion. So that's my ignition temperature. Extinction temperature, that's this curve, and it's basically the same thing, except now I'm operating at a high conversion. What temperature would I have to cool the feed down to in order to go back down to the low part of the steady state, so something down here. So again, just kind of started playing with that. So let's start with like 400. We know where that is, and now we know we have to back that down. So maybe something like 350. Now I've overshot that, so 375. And basically just keep massaging it until I got to 362. So if I'm up here and I gradually turn the feed temperature down, what I'm basically doing is I'm shifting this energy balance curve to the left, where I finally shift it to the left, and I no longer have a point of intersection, so I'm tangent to this part. That is the feed temperature that's going to take my reactor temperature back down, and hence my conversion back down. So that's what's meant. That's what's meant by ignition and extinction. So there's one more thing that I want to talk about when it comes to making these types of plots, and that is G of T and R of T. When we looked at non-isothermal tubular reactors, one of the things that we considered was the heat generated and the heat removed. And we said the heat is generated due to the reaction, and the heat is removed mostly due to the heat exchanger, and then you also have sensible heat effects from the contents in your reactor. And similar thing is true here. For a CSTR, we call the heat generated capital G, and we call the heat removed capital R. Capital G, to the heat generated term, that is equal to the mole balance times the negative heat of reaction. The capital R of T, the heat removed term, that is equal to the energy balance times the negative heat of reaction. So I can plot either way to make my solution. If I look at my X of T curves and my G and R versus T curves, they're essentially the same, except for these curves have been multiplied by negative heat of reaction compared to the X versus T. So G of T looks a lot like my mole balance term. That's because it is my mole balance term multiplied by a number. In fact, it's times the negative heat of reaction. That's the heat generated is due to the reaction, so it makes sense that it would be a scalar of the mole balance. The G of T term, or the R of T term, the heat removal, that's my energy balance times the heat of reaction, or the negative heat of reaction. So either way I can do that. Just something to be aware of, because you'll see these types of problems being solved in both ways. Okay, so the final thing that I want to talk about when it comes to these types of solutions is what influences the R of T term. So we know what influences the G of T term, that's the reaction. But what influences the R of T term? And we said that this is a linear equation. For every R of T term, we could make a slope and a y-intercept. So I've put those values for this equation here, which I've just calculated based on the data here, so nothing fancy. So how do we get those to change? So we know that we can get the y-intercept to change. That's going to be when we shift this term to the left and to the right. So we know we can do that by changing the feed temperature. So if I change the feed temperature, for example, to 400, then my line shifts to the left, whereas I switch it to 500, my line switches to the right. So basically, if I want to switch my curve, or if I want to shift my energy balance curve or my RFT curve, I need to change the feed temperature. So say I said, I don't want to operate at 400 K because that's too hot. How do I operate at a lower temperature? Well, the way to do that would be to decrease my feed temperature. In fact, if I decrease to 425, I would be operating at closer to 390 in my reactor. So that's how I do that. If I want to change my slope, there's a number of values that play into that. The one that has the greatest contribution is the UA term. So if you look at the slope right now, the RFT term has a slope of 150. If I want to change that, I can change this value. So I change UA from 8,000 to 9,000. Now I have a slope of 162.5. So I'm shifting, I'm basically rotating, I'm basically rotating that RFT term so that it's becoming more and more perpendicular. And then if I decrease the heat exchanger term, then I get a smaller slope. So I'm flattening out that line. So you notice, too, that makes sense. If I use my original value for UA was 8,000. If I make it 6,000, that means for the same feed temperature, I operate inside the reactor at a higher temperature. Whereas if I operate with a higher heat exchanger term, I operate at a lower temperature. So the heat exchanger, the heat transfer coefficient also plays a significant role in what the reactor temperature will be. So that's another thing to consider, is the heat exchanger term, and if a reactor temperature needs to be a certain value, what heat exchanger term can be used to accomplish that. And that is all I want to say about this particular problem.